On the 7th of July 2026, Google published a research paper in the journal Nature that took a genuinely bizarre calculation and made it real. A quantum chip called Willow, sitting in a lab in Santa Barbara, California, had just finished running an algorithm called quantum echoes. It took the chip roughly 5 minutes to run the exact same calculation on Frontier, currently one of the fastest classical supercomputers ever built, housed at Oak Ridge National Laboratory in Tennessee and capable of over a quintillion calculations per second. Would take, according to Google's own published estimate, 10 septillion years. That's a 10 followed by 24 zeros. The universe itself is only about 14 billion years old, so that number isn't just large. It's meaningless in any everyday sense. A comparison so lopsided it barely functions as a comparison at all anymore. More like two entirely different categories of thing being awkwardly forced to share the same unit of measurement. And this wasn't a demonstration run on some artificial, cherry-picked benchmark designed purely to make quantum computers look impressive on paper, the kind of contrived mathematical puzzle that's defined most quantum computing headlines for the better part of a decade. This was, for the first time in the history of the field, a verifiable result, meaning independent scientists could check the answer and confirm it was actually correct on a calculation with a practical scientific use, mapping the physical structure of a molecule to understand why that specific combination genuinely useful, genuinely faster, and genuinely checkable. ICE is such a big deal, and why it landed as one of the most significant moments in the entire history of quantum computing. You need to understand what's actually been happening inside Google's quantum lab over the past 2 years, because this result didn't come out of nowhere. It's the payoff of a problem physicists spent nearly 30 years failing to solve. Quantum computers work in a way that's fundamentally structurally different from the laptop or phone you're reading this on. A normal computer stores information as bits, saying each one either a 0 or a 1, nothing in between. With every single calculation your phone has ever run, from loading a web page to editing a photo, ultimately reducible to enormously long chains of those simple binary switches flicking on and off. A quantum computer uses qubits instead, and thanks to a genuinely strange property of quantum mechanics called superposition, a qubit can exist in a blend of 0 and 1 simultaneously, not as some philosophical trick or rounding error, but as a real, measurable physical state that's been experimentally confirmed for the better part of a century. Link enough qubits together through another quantum property called entanglement, where the state of one qubit becomes intrinsically linked to the state of another regardless of the physical distance separating them, a phenomenon so counterintuitive that Einstein himself famously and dismissively called it spooky action at a distance, and you get a system that can, in principle, explore an enormous number of possible answers to a problem all at once, rather than checking them one at a time the way a classical computer has to. That's the theoretical promise that's been driving quantum computing research since physicist Richard Feynman first floated the basic idea back in the early 1980s, arguing that if nature itself runs on quantum mechanical rules, then simulating nature accurately might genuinely require a computer built on those same underlying rules, rather than the classical logic every computer since has relied on. The problem, for nearly the entire history of the field since then, has been keeping those fragile qubits stable long enough to actually do anything useful with them. Qubits are almost absurdly sensitive, considerably more so than most popular explanations of quantum computing tend to convey. A stray cosmic ray passing through the lab. A tiny fluctuation in temperature measured in thousandths of a single degree. Even faint electromagnetic interference bleeding in from equipment sitting in the next room. Or vibrations from someone walking past the wrong section of the building. Any of these can knock a qubit out of its delicate quantum state, an event physicists call decoherence. And once that happens, whatever calculation was running simply falls apart, corrupted by noise, forcing the whole process to start over from scratch. For decades, the obvious fix, adding more qubits to build in redundancy, the way classical computers use error-correcting code to catch and fix the occasional flip bit, actually made the problem worse rather than better in a quantum system. More qubits meant more individual points of failure, and past a certain scale, the system would generate errors faster than any correction process could realistically fix them. A runaway problem that essentially capped how large and how useful any quantum computer could become. Physicists called this the error threshold, and it functioned for the better part of 30 years as an invisible wall standing between quantum computing as an interesting laboratory curiosity, good for winning academic prizes and generating impressive-sounding headlines, and quantum computing as a genuinely useful, scalable technology capable of solving problems nobody could solve any other way. In December 2024, Google's Willow chip broke through that wall for the first time. In a result the company described at the time as solving a problem that had challenged the field for almost 3 decades. using a technique called the surface code, where multiple physical qubits are grouped together to function collectively as a single, far more stable logical qubit. Google's researchers demonstrated something that had never been convincingly shown before, that as they made the grid of physical qubits larger, moving from a 3x3 grid up to a 5x5, and then a 7x7, the overall error rate of the resulting logical qubit actually went down instead of up. That's the specific technical milestone researchers call going below threshold. And it matters enormously because it flips the entire logic of scaling a quantum computer on its head. Instead of every additional qubit being one more potential point of catastrophic failure, adding more qubits, arranged the right way, becomes a source of increasing stability. It's the difference between a house of cards that gets shakier every time you add a card and one that somehow gets sturdier the taller you build it. Once that principle is proven, scaling up stops being a series of miracles and starts being, in the words of researchers close to the project, a genuinely predictable engineering problem, the kind you solve with more careful manufacturing and better materials rather than some undiscovered breakthrough in physics itself. That below-threshold result was the foundation. Quantum echoes, the algorithm behind that July 2026 Nature paper, is the first major payoff built on top of it. Technically, the algorithm is known as an out-of-order time correlator, or OTOC, and what it actually does is measure how a tiny disturbance introduced at one point in a complex quantum system spreads outward and scrambles the rest of the system over time. A phenomenon that shows up in contexts ranging from the behavior of individual molecules to, more speculatively, the physics of black holes. Google's team ran the algorithm on real molecules and compared the results directly against an entirely separate, well-established experimental technique called nuclear magnetic resonance, or NMR, the same basic physical principle used in every hospital MRI scanner on Earth. The quantum computer's answers matched the NMR results, and did so while extracting more precise structural information about molecular geometry than the conventional method could manage on its own, effectively functioning as what Google's own researchers described as a molecular ruler, capable of measuring distances inside a molecule with a level of detail existing techniques struggle to match. That combination of verified accuracy, genuine practical output, and a speed advantage so large it borders on the absurd is what separates this specific result from basically every previous quantum computing headline of the last several years, and most of which involved contrived, deliberately obscure mathematical problems with no real-world application at all, designed purely to demonstrate that a quantum processor could technically outperform a classical one on anything. Google isn't stopping at proving the concept either, and the roadmap it's laid out gives a genuinely useful sense of just how quickly this field is currently moving. The company has published a formal 6-stage hardware roadmap, and having demonstrated below-threshold error correction, it's now working toward what it calls milestone 3, a single, long-lived logical qubit, stable enough to hold its quantum state reliably for extended periods, the essential building block needed before you can start chaining logical qubits together into something resembling a genuinely general purpose. A fault-tolerant quantum computer capable of running arbitrarily long, arbitrarily complex programs the way a classical computer can today. And in March 2026, Google made a move that quietly signaled just how seriously it's now treating the race to get there. For more than a decade, the company had bet almost entirely on one specific hardware approach, superconducting qubits, tiny circuits cooled to within a fraction of a degree of absolute zero, the same underlying technology behind both the 2019 Sycamore chip, which first demonstrated a quantum computer solving a problem beyond the reach of classical machines, and the Willow chip that followed it. In March, Google announced it was adding an entirely second hardware approach to its research program, neutral atom quantum computing, a technique where individual atoms are trapped and precisely arranged using focused laser beams, sometimes called optical tweezers, with each individual atom itself functioning as a qubit. Hartmut Nevin, the founder and head of Google Quantum AI, explained the logic behind running 2 different hardware strategies in parallel, using a genuinely elegant piece of shorthand. Superconducting processors, he said, are easier to scale in the time dimension, meaning they can run deep, fast circuits, while neutral atom systems are easier to scale in the space dimension, meaning they can pack in a much larger raw number of qubits, with neutral atom arrays already reaching roughly 10,000 individual atoms, an order of magnitude beyond what any single superconducting chip has managed, though those systems currently operate on considerably slower millisecond scale cycle times compared to the superconducting approach. Betting on both approaches simultaneously means insights and engineering breakthroughs made in one hardware lane can potentially be applied to accelerate the other, hedging against the very real possibility that no single quantum hardware architecture ends up dominating the field the way silicon transistors eventually dominated classical computing, and the neutral atom program has already drawn on close collaboration. With Quera, an outside startup specializing in the approach, alongside deep ties to the atomic physics research community centered around Boulder, Colorado, including the University of Colorado Boulder, the Gila Research Institute, and the National Institute of Standards and Technology. This is also where quantum computing and artificial intelligence have started to genuinely merge into a single, self-reinforcing research effort, rather than remaining two separate fields that occasionally reference each other in press releases. A separate but closely related breakthrough, reported around the same period by a team including researchers who had previously worked directly inside Google's own quantum lab before departing to co-found an independent quantum computing startup called Oratomic, showed AI playing a direct, acknowledged role in accelerating quantum algorithm design itself. One of the researchers involved put it about as plainly as a scientist ever does in an interview, stating flatly that there was no question at all that artificial intelligence had been used to accelerate the specific development in question. The mechanism works in both directions simultaneously, and it's a genuinely interesting feedback loop once you see it laid out. Better, more capable AI models can help physicists design smarter quantum error correction codes and predict exactly when and where a qubit is likely to experience noise before that noise actually corrupts a calculation, using what are effectively small, specialized language models to continuously monitor and calibrate the physical qubits in real time, adjusting control signals on the fly to compensate for noise before it has a chance to derail an ongoing computation. At the same time, sufficiently powerful, error-corrected quantum computers are expected, further down the line, to eventually help train and run entirely new classes of AI models more efficiently than any classical supercomputer could manage, particularly for problems in chemistry, materials science, and complex physical simulation, the exact kind of task Quantum Echoes has now shown real, verified promise on. Researchers in the field describe this as being at the very beginning of that particular cycle, right now, better AI helping design better quantum hardware, which in turn helps train better AI, feeding back into itself with no obvious ceiling yet in sight, a genuinely open-ended dynamic that several people working closest to it describe as one of the more staggering, still not fully appreciated implications of where this research is actually heading. Now, for the part of this story that genuinely does carry the kind of high-stakes urgency that headlines love to reach for, and in this specific case, the underlying concern is real, not manufactured for clicks. Quantum computers, if they ever become powerful and stable enough, pose a direct, well-understood threat to the encryption protecting almost everything sensitive currently moving across the internet, from ordinary WhatsApp messages to classified government communications to the cryptographic keys securing cryptocurrency wallets, banking systems, and national infrastructure alike. The specific danger comes from an algorithm called Shor's algorithm, first devised by mathematician Peter Shor back in 1994, long before any hardware existed that could actually run it, which shows, mathematically, exactly how a sufficiently powerful quantum computer could rapidly factor the enormous prime numbers that current encryption standards rely on. A calculation that would take even the most powerful classical supercomputer on Earth far longer than the age of the universe to crack through brute force alone, but that a large enough, stable enough quantum computer could, in principle, solve in a matter of minutes, essentially rendering the entire mathematical foundation of modern digital security obsolete overnight, everywhere, simultaneously, the moment such a machine actually exists and is turned on. For years, the reassuring consensus among cryptographers was that actually building a quantum computer capable of running Shor's algorithm at the scale needed to break real-world encryption would require somewhere between 10 million and over 300 million physical qubits, a genuinely enormous, decades-away engineering target that let most of the internet's existing security infrastructure treat the whole threat as a distant, comfortably theoretical problem, something to plan for cautiously over the coming decade, rather than something demanding urgent, immediate action. Google's own more recent published research has significantly narrowed that gap, and narrowed it fast enough to catch much of the cybersecurity industry visibly off guard. According to a white paper detailing roughly a 20 times efficiency improvement in how Shor's algorithm can actually be implemented on real hardware, achieved through smarter, more efficient circuit design rather than any change to the underlying mathematics Shor originally worked out, that previously enormous qubit requirement has fallen to under 500,000 physical qubits. A target that, while still genuinely far beyond what any quantum computer on Earth can currently do, no longer sits comfortably in the realm of distant science fiction the way it did even 2 years ago. That single revision sent a visible shockwave through the cybersecurity industry. Bas Westerban, a cybersecurity researcher at Cloudflare, a company that secures a meaningful fraction of the entire internet's traffic, told reporters plainly that it was a real shock, and that his own industry would need to significantly speed up its preparations. Cloudflare responded by publicly accelerating its own internal deadline for migrating to Post. Quantum encryption standards, the kind specifically designed to resist a quantum attack using entirely different mathematical foundations than the ones Shor's algorithm targets to 2029, 6 years ahead of the original 2035 deadline previously set by the American National Institute of Standards and Technology. Google itself, separately, announced its own internal target of fully securing its own systems against a future quantum attack by that same year, 2029, effectively racing to protect its own infrastructure against the very technology its own research division is simultaneously racing to build. There's a specific, uniquely vulnerable category of digital asset sitting directly in the crosshairs of this accelerated timeline, and it's worth understanding exactly why, because it illustrates the threat in genuinely concrete terms rather than abstract cryptographic theory. Most modern cryptocurrency wallets are reasonably well protected because the actual public cryptographic key needed to attempt this kind of quantum attack typically only becomes visible on the public blockchain at the exact moment a transaction is broadcast, giving a would-be attacker only a narrow window, often just minutes, to act before the transaction is confirmed and settled. But a meaningful portion of the total Bitcoin currently in circulation, estimated at somewhere around 32%, close to 7 million individual coins, sits in older-style wallet addresses, where the public key has already been permanently exposed on the blockchain for years, simply as a consequence of how those particular addresses were originally set up. Long before this specific quantum vulnerability was well understood by the people originally designing early cryptocurrency wallet standards. Those specific coins, sitting in older, already exposed wallets, represent a meaningfully more attractive and more immediately vulnerable target the moment a sufficiently powerful quantum computer actually exists, compared to funds held in more modern wallet formats where the public key stays hidden until the very moment it's actually spent, giving those newer wallets at least some structural protection that older ones simply never had built in. It's genuinely important, though, to hold two separate facts in your head at once here, rather than sliding straight into pure panic, because that's exactly where a lot of less careful coverage of this story tends to go, and it's worth resisting that pull deliberately. The first fact is that this threat is real, increasingly well quantified by legitimate published research, and already being treated with genuine seriousness by major cybersecurity companies and national standards bodies alike, not dismissed as hype or exaggerated marketing from a company with an obvious commercial interest in making its own research sound as dramatic as possible. The second fact is that a 500,000 qubit, fully error-corrected, genuinely stable quantum computer capable of actually executing this specific attack does not currently exist anywhere on Earth. And building one remains a formidable, multi-year engineering challenge, even with Google's own below-threshold breakthrough now firmly in hand, requiring not just raw qubit count, but also the kind of long, stable coherence times, precise control electronics, and manufacturing consistency that no lab, including Google's own, has yet demonstrated at anywhere near that scale. Even Google's own most recent public roadmap points toward the current decade's end, not tomorrow, as the point where commercially relevant, large-scale quantum machines might realistically emerge, and Google itself has stated it remains confident in that broader superconducting timeline, even as it now hedges its bets with the newer neutral atom program running alongside it. Independent quantum researchers outside Google, including academics at institutions like Princeton, have specifically cautioned that some of the more dramatic efficiency claims circulating in this space rely on assumptions about future qubit quality that remain genuinely untested in practice, and that reducing the theoretical qubit count needed for an attack on paper is very different from actually possessing physical hardware capable of running that attack reliably at scale. Without falling apart from noise and decoherence partway through the calculation, a gap between mathematical possibility and physical reality that has, historically, taken quantum computing considerably longer to close than early optimistic timelines tended to predict. That tension, real and urgent on one hand, still genuinely years away on the other, is exactly why serious voices inside the field have converged on the same basic piece of advice rather than either extreme. Encrypted data intercepted and simply stored today by a patient. A well-resourced adversary could, in principle, still be decrypted retroactively once a sufficiently powerful quantum computer eventually exists years from now, a strategy security researchers have started calling harvest now, decrypt later, and it's precisely that specific risk, rather than any immediate present-day vulnerability, that's driving the accelerated migration timelines now being adopted across the industry. Waiting until a functioning large-scale quantum computer is actually sitting in a data center somewhere before beginning, that migration would already be too late for any sensitive data intercepted and quietly stockpiled in the meantime, which is exactly why organizations like Cloudflare and Google itself have chosen to treat 2029 as a hard deadline rather than a comfortable, distant target they can revisit later. So, what does all of this actually add up to as of the middle of 2026? Google has genuinely, verifiably crossed a threshold in quantum error correction that the entire field spent nearly 30 years trying and failing to reach, and it followed that breakthrough with the first quantum computing result that's simultaneously faster than any classical alternative, independently checkable by other scientists, and directly useful for real scientific work, not just an abstract proof of concept designed to win a press cycle. It's expanding its hardware strategy onto two entirely separate technological tracks simultaneously, hedging its bets on which underlying physical approach ultimately wins out. It's leaning increasingly on artificial intelligence itself to accelerate the extremely difficult engineering problem of building and calibrating the hardware, creating a genuine, self-reinforcing feedback loop between two of the most consequential technologies currently being developed anywhere on the planet. And it's forced, through its own published research into more efficient code-breaking algorithms, a very real, very serious global reassessment of exactly how much runway the world's existing digital security infrastructure actually has left before quantum computers stop being a theoretical, comfortably distant concern and start being a genuine, practical one. None of that requires exaggeration, and none of it needs a breathless headline claiming physics itself has somehow been broken to land as one of the most consequential technology stories of the year. A machine finishing, in 5 verified minutes, a calculation that would otherwise take 10 septillion years, using hardware that, by the laws of physics as we understood them just 3 decades ago, genuinely wasn't supposed to be able to stay stable long enough to attempt it at all. Doesn't need any embellishment. It's already, on its own terms, one of the strangest and most significant scientific milestones of the decade.